Hello guys, let me know if you can hear me properly before we start. You might actually not hear me because my mic is on mute, or no. Okay, this should be fine. Just let me know if you can hear me properly, and then we'll begin as soon as possible. Is everything all right? Okay, we're starting to hear some responses from you, which sounds good. So if you can hear me properly, if everything's good, then I guess it's good. It's good to start. Okay. So let's see, what are we going to start with? So we have a problem J here that is like the next one on the list. Obviously, the first two are like general stuff. I'm thinking of, so the idea is that we have some problems here that we might try to solve today, and we also have a problem here that's from the last stream, but we haven't solved it. So yeah, I guess we're good to go. Let's see if we can start with like an easy problem actually first. So I can see that there's like a problem C, a problem D. Let's actually look at problem J here and let's see what this is about. So problem J, as always, you can follow this link to look for it for yourself and try to solve it yourself. We are going to try to solve problem J, jealous split, from 300 IQ contest 1. So this contest, let's make sure that we haven't solved it. It's been solved by 12 teams. I guess it might be a hard problem, so we'll keep it like for later, but we'll think about it. I just want to start with an easier problem first. So problem J will probably be on the list, but like later rather than sooner. So let's see this problem D, or at quarter grade contest problem D also sounds like hard problem. Let's try this div1a. So being div1a, it should be more simple than not. I hope so. So let's see. So for now, we'll solve problem E from Codeforces. It's div1. Div1e also kind of like a harder problem. Is it? Like it's supposed to be easy problem, right? Easy implementation div1e, but the problem, oh, it seems that this link is the same as this link, so it's kind of like wrong link here. So let's try this one that's actually a div1a. So we'll start with div1a and we'll slowly increase our difficulty. That's like the goal for today. Okay. Next time, create a separate poll. Looks like it's mixed with the previous one. Yes, it is mixed with the previous one. What I did is I erased the problems that I have solved from the last poll and kept them. So, yeah. Okay. Cool. So let's start by reading problem A from this Div1 contest 601. Code forces. Just give me 1 second. Give me one minute. Each cell of the farm is assigned to exactly 1 chicken. Forms a connected area. Difference between the maximum and the minimum number of cells with rice to be as small as possible. Each cell of the farm is assigned. Okay, let me try to kind of take some notes about the statement. So we have we seem to have a rectangular grid of arrows and C columns, and we have K chickens, and cells are empty or with rice, right? So this would be empty cells. So the dots will be empty cells, and the R's will be cells with rice, and we have to assign cells to chickens. So each cell is assigned to exactly 1 chicken. Okay, whether it's free or not, it seems from the drawing. So we have to kind of like have like connected the regions assigned to each chicken. Okay, a set of the cells and different cells with rice. Okay, so we have some cells that have rice and some chickens. Here we seem to have 3 chickens and 3 cells with rice. So the idea would be to assign only 1 cell of rice to each chicken. So the way I usually try to tackle these kind of problems, or like the first idea that comes to mind when I'm trying to tackle this problem, at least, is to figure out, like, obviously the minimum difference between the maximum number of cells with rice and the minimum number of cells with rice is either 0 when the number of chickens is like a divisor of the number of rice. So here the minimum possible difference that you can have while assigning these is 0, because like in a best scenario you would assign each chicken one rice field. But if you have something like, let's see something different, maybe these examples aren't the greatest. Here you can see that it seems that some chickens are assigned 3 rice fields, some chickens are assigned 2 rice fields. So the condition for that to happen is that the number of rice fields is not divisible by number of chickens. This, like, the minimum difference is 1, and else it should be 0. Now the question here is, can we always obtain this answer? So this is like the best answer that we can ever obtain. The question now is, can we obtain this answer? My guess is that you can. Now, how can we prove it? One way to prove it is to actually construct the sequence. Like, I'm pretty sure that you can, because if you couldn't, the problem would seem very difficult for a div1a. So I'm assuming that you can. And if you can, usually what you can do is you can either try to try to come up with some proof of it that might involve induction, or just construct it straight away. So let's see. Basically, if our target is difference 0 or difference 1, then it means that if we consider the first chicken, we have to assign it a given number of rice cells. Like, let's say, I don't know. Let's say for the first chicken, I want to assign it 1 rice, for the second chicken 1 rice, for the third chicken 1 rice. If it's 1, it's easy. What happens if it's 2? Is there a good way of assigning stuff? I think it might be. So what I'm thinking is something like that. If you have the matrix, let's say, okay, imagine this is the matrix and it has, I will draw some rice fields along the way. Rice, 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 rice. Now imagine going through this matrix in like snake order. Like, go from the top left corner and go right, 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 and then down, and then left, and then down and right again, and down and left again. If you think about it, this will kind of transform the matrix into a 2D row, which will have row R, R, R. So it's like going here and then going down, and here, down, here, down, here. Why I do that is because I'm thinking that if I can do that, then it means that I could assign segments to each chicken that because like this traverser is in snake order, it would be connected. So we have no problem of connectedness, and because now I'm not solving the problem on a matrix, I'm solving it on an array of numbers, it's obviously easier. So it's like it's a lot easier to assign each chicken to however many rice fields we want. So that's actually what we'll do. Now, what's like what we have to output here? 1, 2, 3, ABC. So let's see like the output. For each test case, airlines, lowercase and a digit equal. Okay. Okay, so it seems like it doesn't matter which characters we assign it. We just want to encode the zone. Okay, seems pretty solvable at this point. So let's start trying to code it. So let's do problem 1, or how did I call it in the beginning? Like in the first stream, I don't remember. Let's write some pretty skeleton code. Okay, and now, first reading the input, it should be simple, t test cases. A lot of misspells today, sorry about that. And mk for read the matrix. Cool. So now we have the matrix, and that should be fine. Now, what we would want to do is we would want to enumerate like all the rows. So let's see. We have k. Let's first count the number of rice. This should prove handy in the later stages. So now we have counted the number of rice cells. Another thing that we want to do is we want to know how many rice cells we want to assign for each chicken, right? So let's see how would we do that. Let's assign a vertex target that has k elements is initially 0, and for each element, target of I equals rice divided by k, and for let's see, this should be rice mod k, target of I plus equals 1. And let's just check it to be sure. So let's just analyze this code a little bit, what I've written. So the first thing, I just read the matrix and computed the number of rice cells in the matrix. And this target will tell me for like the ith chicken how many rice cells I want to assign to it. And this is just like a checksum to make sure that I assign all the rice cells to all the chickens. And now I have to basically try to compute the solution. So vector string sol and vector string, no, it's actually string of m and dot. So here we'll build our solution. And now we have to basically traverse the matrix in snake order and assign stuff to sol. And let's see what the alphabet should be. K is up to 62. So how would we do that? String alphabet for alphabet actually this should be char, but same stuff. This should be char and this should be char. Cool. So now we have all the alphabets, and alphabet resize k, just to make sure that this alphabet will just tell us which character we will output for the ith chicken. And now what we will do for let's, if I so is 0, here we'll just do like the, how do we say, like the snake traversal of the matrix. So what we have is int at 0, int count of rice cells is 0. So if I will do for j from 0 to m, and else we'll do the same thing for j m-1 to 0, m-1 through 0. Cool. And now what we write inside these for loops is like assigning the rice cells to the to the cell. So if we'll say, wait, solution of ij equals alphabet of at, and if met of ij is a rice, plus plus cnt, and if cnt equals like the rice target of at plus plus at. And we should do the same here. Oops. Oh shit, now I have to write it all over again. Oh well, because I don't know how to redo in like Vim. I am very bad at Vim, and I don't know how to redo stuff. So I undid some stuff. Now I have to write it again, just so that you know how non-productive I am at Vim. Let's actually keep this as well. Like a friend of mine told me to keep the notes as well. So let's see what were we writing. So solution of ij equals alphabet of at, and if met of ij equals r, cnt plus equals 1 if cnt equals target at plus plus at. Now we wanted to copy this here and paste it here. So this should be it. Now, looking at this code, I have one extra thing to mention. What happens at the end, like if we've reached the target for all of these things. Now, the thing is, like at here will kind of, it's a bit hard to explain. So when I reach the last rice field, I will get this at to be equal to k, and it will probably crash at this. So like one quick fix for this, I guess, is to just do target back plus equals 1 here. Let's do it here. This will make sure that we will never reach our goal for the last chicken, so we will assign all the cells to the last chicken, even if the last chicken has already reached its goal. Okay, this seems to be it. Now all we have to do is just output solution of I. Let's see, is this how we want to output? It seems like it. Okay. So this should be all the code. Let's compile it and test it. Okay, it compiled successfully. That doesn't necessarily mean that it will also run successfully. Oops. Okay, let's check what happened here. Obviously the last thing doesn't seem right. The first thing also seems ABB, so it's only A and B. Why is that happening? Okay, let's copy this to an input file and examine, debug a little bit of the task. Okay, so first so this is like the first output, and the expected output should obviously have 3 chickens. So this is bad. Why is that? Is because here I missed something. I missed setting CNT to 0. CNT is 0. Cool. Let's try to run it again. Now it seems more like it. It seems like we actually have what we are expecting to have. So we have everything through 9, B, 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 obviously good. And now we go with C. Okay, I'm pretty happy with this solution, so I guess I will just straight up copy it and just see what happens. So let's see. Copy and submit it. Feeding chicken. Some other people are actually also trying to solve problems on Codeforces, which is great. Okay, it's running on test 14. It got accepted. So, okay, first problem got accepted. We are happy. Let's move on. Okay, how do we undo? That's actually good tutorial from your part, guys. Can I make the stream 180p? I will make the stream next time. I will make it 180p. I'm sorry, for now it's recorded on something like 1440 on 900, so I will do that for the third stream. Any drawing tool instead of pen and paper. Okay, so about the drawing tool, the thing is that it's hard to draw with the mouse or with the touchpad, so I will need some sort of tablet, like Wacom tablet for that. I will probably buy one soon, but until then, like pen and paper seems to be the best option, like the best alternative. Okay, so we are done with this problem. We can mark it as solved. Do you have any suggestions for what I should do next? If not, probably I will. I will try one problem from Info Arena. Have I solved this one? Maybe I think I have solved this one, right? I've solved this one on the last stream. So maybe another problem on Info Arena, maybe something from here. So any suggestions on your part? Anything you want me to see solving? If not, we will move on. Maybe even, I don't know, this J? We can read it. I mean, we don't have to solve it right now. We can just read it and think about whether or not we have an idea. An array of integers. This seems like an interesting task. Also pretty hard task. Hey, can you solve this Google Kickstart question? Do you have like the actual question? Other task that we can solve is this. Let's see. Problem D, it has been solved by 26 teams, so it seems like it's not like the worst problem to pick as next. We can also try to read this one as well. So we have a game theory. We have provided a link above. Sorry, I don't seem to see the link. I don't seem to see the link. Have you provided it in the chat? Like I'm looking at the chat right now, but I don't see the link. Or 758F on Code Forces. Let's try this one. 8F. No, 758. Okay. Contests. No. Are you sure it was 758? geometrical progression. Number of distinct geometrical progressions contains n distinct integers not less than L and not greater than R, and L and R are rather big numbers. Six, 7 and 7, 6, so it seems like a progression can be ordered in any way. Should we do this one? Can I share my vim.rc file? Yes, sure. I can do that actually. It's like, so this is my vim.rc file. Enjoy. Okay, let's see if we can solve. Well, I'll try to think about it for this, like think about this problem, and then maybe I will move into a different problem, maybe this one. This one is div1e, but it's supposed to be an easy div1e problem. I'm a bit anxious about div1e problems as our second choice. So I will first try to think about this one. It doesn't seem that hard. So AI. So for this problem, what I'm thinking, like, first of all, it seems like I might be wrong here, but it seems like n cannot be that big, because if you have a ratio, so for example, if ratio is 1, so if ratio is 1, then the geometrical progressions would be A. So this is banned. This is not what we want. So ratio should be different than 1. Now if ratio is less than 1 and all of them are between R and R, we can just invert it and just like if the progression is a times r squared and a times r to the n minus 1, we can just revert it and consider this to be the first element and to have a ratio which is bigger than 1. So like the geometrical progressions with ratio less than 1 are in bijection with the geometrical progressions of ratio 1 over r, so bigger than 1. So we can just assume that ratio is bigger than 1. Now the ratio, as they say, is something like a divided by b. And now let's suppose obviously that this ratio is a rational number, so we can suppose that a and B are coprime. And if A and B are coprime, that means that an element, let's call it, I don't know, let's call it X, or X divided by I, xi, y, because I suppose that the first element is A. So an element is like A times x to the I over y to the I, and because x and I are coprime, it seems like A has to divide y to the ith power, and in order for it to divide y to the ith power, there's like A should also be very big, like A should have the prime factors of y to the ith power. So like if n is 10 to the something big, it's not that possible. There's also like a different case where y is 1. So like if ratio is an integer, but if ratio is an integer and greater than 1, it's at least 2. So it also cannot be that big. So my assumption is that n can be considered, like if n is greater than, let's say, let's calculate it a little bit. Let's say n greater than 26 or n greater than 30, then the answer is 0. So we can assume that n is small here. That's like the first observation. Yes, G++11 is an alias, which is in bash source. It's just G++ with some optimization, with some compilation. Like, let me actually show it to you. It's in bash rc. So it's actually, wait, alias G++11. Okay, so this is like the alias that I'm using for G++11. So cool. If n is greater than 30, then the answer is 0. So now n is small. We still, like, the problem is that we might, like, if we iterate over let's say A, and yeah, and see how many ratios are with the first element A. Is this a great thing to do? N is not very big, so the only it seems like the only thing that we have to check, like if we iterate over A, is that A times r to the n minus 1 should be less than or equal to r. Of course, given that our r is greater than 1. So what does that mean? It means like the lower, like the b, the y of this ratio should contain prime numbers, like should be a divisor of A, and it should contain numbers from, okay, that's actually, that might actually work. It seems like the total answer is small, like the number that we output here, the answer to the problem is rather small. So if we have A times, if we fix B, it shouldn't have many values. It should be a divisor of A. For seconds. So n log n might work, I guess. I guess n log n is an option here. If not, we can do some optimizations to make it pass. Okay, I think I have some rough idea on how this might work. Just give me one more second. So we fix A. Okay, so I found out some things on paper about this. Obviously, n isn't that big here. Okay, so that's like the first thing. And now if say we fix a and y, so y is the here this thing on the on the denominator, I think it's called, or not, the thing on the right hand side of the division sign. So if we fix a and y should also be a divisor of a. So actually y to the n minus 1 should divide a. And if this happens, then x can take a range of values. Obviously x has to be greater than y, and a times x to the n minus 1 divided by y to the n minus 1 should be less than or equal to r. So like if y is big, then x cannot have a lot of values, right? Because this grows rapidly. This is like exponential. So even if a divided by y to the n minus 1 is 1, then x cannot take a lot of values if y is at least 2, let's say, because like if y is 1, we can try to figure something out. Even if y is 1, then this x to the n minus 1, there's not many values that it can have. So yeah, I think like at this point we could just iterate over a. Do we want to iterate over a? Like if we iterate over a, then all elements are divisible by a, or no? So yeah, we can iterate over a and iterate over y, which shouldn't be that big, because like y to the n minus 1 has to be a divisor of a. And just iterate over x again. I think this might just solve this problem. So let's see. Let's solve prob 2. We'll just figure it out while writing the code, and we can also check the bounds might be a little bit tight, maybe not though. Okay, now what can we do here? We have to read n up to 10 to the 7th, so it's okay. N L R. And now for each x we have to compute. So yeah, let's do the simple thing. If n is greater than 30, greater than or equal to 30, we'll just output 0, which I hope this is the case. We'll have to actually check it. Is this the case? Probably, yeah. Wait, for each progression, I'm just, there's just something that I haven't checked. I want to make sure that the task tells us that all the numbers in the progression have to be integer. Number of distinct geometrical progressions, then distinct integers. Okay, so all of them have to be integers, so we're actually good. If n equals 1, if n equals 1, then the answer is r minus l plus 1, because like this is just some optimizations that might come in handy. Like for example, if n is very small, then my solution might be too slow, so I'm just hard coding some cases. If n equals 2, then all progressions of l minus r plus 1 things are viable, so the answer would be l minus, so wait, let's make sure we don't screw this up. So l r, so it's r minus l plus 1 minus len. So this should be fine for the case of n equals 2, and for n greater than 2, I assume that the total answer would be small. Is that true? I mean, why did I say that? Because we have like, if n is greater than 2, the last number is a times x to the n minus 1 divided by y to the n minus 1. And what I supposed here is that if n is at least 3, then this is y to the second power. I guess so. Let me just check. I'm just checking right now to see that there's actually a handful of solutions here, like just not so many solutions. Seems that y has to be divisible, so we consider okay. Okay, so numbers that maybe this will work. I'm actually not sure anymore if this is like good complexity. Let's see. So here we assume ratio is greater than 1. So for each number can be up to 10 to the 7th. Can we go through its divisors? Let's figure out the divisors. D times D. Is it fine? Is it fine? Is it fine? Greatest divisor. Okay. I'm not actually sure that the total complexity will be good, but we can just try. So small would be the smallest prime number that we can divide. Okay. R plus plus R. If small of R is equal to 1, then R is prime. If small of I, then I is prime. If for J is J plus equals I, small of J, if it's 1, small of J equals I. Okay, so this should allow us to factorize. So here we can factorize A in logarithmic time, which is good. And we only want to keep a B that is divisible by, so we have to find highest D such that D to the n minus 1 divides A. And how we do that? We do that using the prime decomposition of A. So int ox, while ox int p equals small of ox, int e equals 0, while ox e plus equals 1, and if e and e equals n minus 1. So now we have to we have computed the highest D such that D to the n minus 1 divides A. And I think that if we have done that, guys, then we can just suppose that this D will be like the denominator. So we can suppose that D is the denominator, and we just iterate over. So D is actually the Y, is the only Y that matters. And now the denominator, we just have to, here we have to compute the highest x such that x greater than D, highest x such that actually x times x, A times x to the n minus 1 over d to the n minus 1 is up to r. Should we do binary search here, or can we just iterate? Well, I think we can just iterate. I think we can just iterate here. Like, the thing is, I think we can just iterate. So int val, let's see, a prime. So a prime equals a over ox. So this is a divided by d to the n minus 1. And now, yeah, we'll just do y here and highest d such that, so like, the thing is, we compute highest y such that this thing, and then d equals y to the n minus 1, as the way I've written this is like this. So we kind of compute highest y such that y to the n minus 1 divides a, which is like we do prime decomposition, and then here we sort of do what I'm describing, and then d is not actually y, d is y to the n minus 1. So if we do a divided by d here, this should give us a divided by 1 to the n minus 1. And now, yeah, we can just assert that a d is 0, and then do a divided by d, and then this number should be greater than or equal to 1 because of reasons. And now we can just do for int x equals, should we do logarithmic power? Okay, let's do x from y. So we actually need to do y. So if I percent n minus 1, why do I actually do that? E n minus 1. Y times equal p. And just keep y and forget about this. Okay, I've changed my mind. I now only have y, and now we can do pow of y, which will compute y to the n minus 1. So for x, while ap, so pow of x times ap is plus x, and plus equals 1. Hopefully this will actually do the trick. Might not. Like here, if it doesn't do the trick, we might need to binary search this or just come up with some formula. But I have some intuition, like I have some idea that this thing might actually fit into time limit, because the thing is, like, here is like square root and greater than r, which r can also be big, so this might fit into time limit if we are lucky enough. Okay, mem of will r plus 1 minus 1 if mem of x not minus 1, mem of x, and then for less times equal x if res greater than r, break. Let's do 1 in 9 here. Why not? Why not? Probably here we will also need to make sure that it doesn't overflow. Okay, so what I've written here, some test cases. Hopefully they are good. I will be looking at them. I'll be looking at them again before I submit. So these test cases, and now n is at least 3 and up to 30. So we compute small, like a small vector, which is just a Eratosthenes sieve that allows us to factorize numbers more easily. We compute small of I, the smallest prime number that divides I. This will allow us to factorize again. This mem is this like PW function computes x to the n minus 1, but it's also memoized, so it doesn't compute something twice for a given x. Might come in handy, again, might not be needed, but it's very easy to write something like that. And here we just iterate over a, and we get the highest y such that y to the n minus 1 divides a, and we use that as our denominator. And obviously here we would want to do n times 2 because of reasons, because like here we have 469 and 964, so answer is always divisible by 2, except for when it isn't. I mean, the only time when it isn't divisible by 2 is when n equals 1. So when n equals 1, answer can be odd, but if not, answer is always even, because you can reverse the sequence and it's also geometrical progression. I'm not very happy to run this and see if it works, but why not? Let's try it. Mean of x and 1e9. We don't want it here. We want int 1e9. Prob 2. Okay, 8% d is 0. Why? Because we don't have. Okay, it compiles, and to check this is like first hard-coded case, second hard-coded case, which is okay. Is it hard-coded case? Well, 2. So yeah. Third hard-coded case, which breaks. Okay, it breaks in line 71. Let's see what's happening in line. Actually, let's do some debugging. Size is 11, x is 11. Let's do mem of. Why would I ever compute pow here again? Pow of x. I guess I might want. I might have r plus 2 somewhere, maybe 38, which is not correct. We'll check it, but the things don't seem to break, which is good. So 3, 3, 10 seems to be the easiest case to debug. So we have numbers between 3 and 10, and n is 3. So let's check. A and A with ratio and the ratio is what? X divided by y. So I assume this would be good. Let's see what. So 3 is good with ratio 2. 3, 6. This is not correct. So that is not correct, because like 3, 6, 12. Okay, okay. So 3 times. So why does it do that? Power of x. Mm-hmm. So I suppose 2 is good and 3 is good, which is weird, I guess. So this computes x. Oh, yeah. Oh well. Little bug that cost me a little bit of time. And my dog is making noises. I'm sorry about that. Okay. 3, 3, 10 gives us 2. A lot better. 8, a lot better. Should we submit? Let's actually try one more test. And let's compile it with fast. So, and let's kill these CRs. Now, the thing is, like, for this task, it's very easy to do maximal test, and I'm not very sure that it will pass the maximum test, so I can just give it. The maximum test would be n equals 3 with 1 and 1, 1, 2, 3, 1, 2, 3, 1. Okay, so it seems to be hanging a little bit slow, but so it has 0.9 seconds, so I'm pretty confident that it will pass if I have not made some mistakes with overflow and stuff like that. It should not time limit exceed, so that's what I was testing. F, geometrical progression. Let's submit. Oh, I've actually coded some stuff here. Running. Accepted. So accepted in 1 second. Am I proud of this code? I mean, it wasn't very hard to write, and it seemed to have been written correctly from the first try. So I would say it's pretty good code. I don't know what I would change about it. So the thing is, like, it's very important to see if you can treat some cases that might make your problem run slower. The usual way I do, like, I solve some problems is I consider some cases and exclude them from the beginning. Like, if some cases are easy, I just exclude them and work with different cases. For this example, big N was easy case because it's always 0. You can prove it's always 0. And also, if n equals 1 and n equals 2, it's there's also like easy cases. Why was it important to write special cases for n equals 1 and n equals 2? Well, for n equals 1, I just wrote it. I'm not sure if my solution would work on n equals 1, but for n equals 2, the thing is the answer is pretty big, if you can see here. So like for n equals 2, the answer is big, and I've kind of proven to myself that for n greater than 2, the answer is small enough that you can just iterate it through here. Like here I'm basically doing big O of answer for n greater than 2, and for n equals 2, I just output a formula. My volume is too low. I'm sorry about that. I'm not sure how I will be able to fix it though. Let's see. Properties. I'm not sure. I'm sorry. I will have to look into the stream afterwards. E minus equals, yeah. Oh well. Yeah, I've changed it since then. So I think we have time for one more problem. Let's see which one should we choose. Wait, we started the stream actually 1 hour ago, so there should be time for, there should be plenty of time. Never mind. I thought I was going slow, but yeah, only 1 hour has passed into the stream. Okay, jealous split. Do we want to think about this one now, or what else can we have? We can have this one. Any other? It's okay. I maxed out mine instead. Yeah, I'm kind of sorry about the volume thing. I think it's because of these earbuds, which are very funny. Like, these are Google earbuds or something like that, like from Google Pixel. And these are literally the first pair of earbuds that I actually had to Google on how to wear them, because they have some weird design. I don't know if you've ever had Google earbuds, but it's interesting that I actually had to look it up, like how to properly wear earbuds. Yeah. Am I participating in Hashcode? Yes, I will be. I will be. Let's see. 2019 round H problem name diagonal puzzle. Yeah, I think we could do that. Let's see. Diagonal puzzle. But I'm not actually sure how to, like, if I can just submit. I have to sign in. Oh well. Can I just sign in? Yeah, we can do that. Do we want to solve this? Do we want to solve this though? Let's see. New puzzle for you to solve. Mm-hmm. Oh, this is actually a cool problem. This is actually a really cool problem. And you want to make it all black and case. Okay, so for this you want to have two moves. Okay, I see. Yes, I might actually try to do this problem. This is very cool problem. Congrats. Let's read some more comments. I see. Are you going to take up making videos for good? Well, it's definitely something that I might, like, I am considering doing. I'm trying to see, like, when I stream, to see how many people are responding to the stream, and if people want to hear me talk about competitive programming tasks and try to solve them and explain them, then I might try to do some videos as well. How to practice competitive programming in order to improve rating? That's a very generic question. You just solve problems. That's what you do. And I guess read articles on code forces about, I don't know, other problems that people think are cool. Okay. To be fair, at first sight, I don't seem to have any idea about this problem, so I'm trying to see if I can rephrase it in some different way. So obviously one thing that comes to mind when like toggling stuff on diagonals and whatnot is that you don't want to toggle a diagonal twice, because like the operations are somehow commutative, if that makes sense. And if you choose to toggle a diagonal twice, it's better to have not toggled it at all. So this means that the answer is always at most the number of distinct operations that you might have, which in this case I think it's order of n, something like 4 times n. Another thing that comes to my mind is that actually, so here it's a dot and we want to make it into a hashtag. How can we do that? Well, there's like 2 options for each. So for this dot, there's like 2 options that you can do. You can toggle this diagonal or this other diagonal. So if you think about it, because this is a dot, it means that we have to make exactly one of these 2 operations. We cannot make 2 of them. So, and if this is a hashtag, it means that we have to do either 2 or 0 operations on this diagonal and this diagonal. So that means that if you if you kind of think about some binary of like 1, if I have toggled this diagonal, like for each diagonal, whether it's like that or like that, if you think about assigning numbers to 1 if you toggle it or 0 if you don't toggle it, then basically what a dot is telling you is that the numbers for this diagonal and this diagonal should be different, like one of them should be 0, one of them should be 1. And for this, it tells you that the number of operations on those diagonals should be the same. So it might be hard to write this, but if you think about it in terms of, so if you have a, I don't know, let's actually paste some test case. So let's say you have this test case. What this dot here tells us is that this diagonal must be toggled differently than this diagonal. So if this is 1, if this diagonal is 1, then this diagonal should be 0. And if this diagonal is 1, then the other should be 0. So we have like constraints of, you have, oh, I see. So the diagonals have to either be equal or different. And this means that if you have assigned one diagonal, you can assign all the diagonals that depend on it. Because if you choose to assign this diagonal, it means that you know what the other diagonal here should be. It means that you know what this diagonal should be. And what do you know? Well, you seem to know all the black squares on the chessboard. So like there seems to be only 2 options, if I'm not mistaken, for every like to solve the points inside the black dots. Okay, so I see. So there's actually like only 4 different solutions that make sense. Can there be impossible? You are guaranteed that it is possible to make all the squares black. Okay, I see. So if we toggle this, if we choose to toggle this, then we know all of these things. And in what order should we process them? Well, I guess, I'm thinking about what order is best to process them, but maybe we can just forget about this and just compute a graph. Yeah, let's just compute a graph and do some sort of connected components. That seems to be easiest. Okay, so it seems that the number of candidate solutions, like the number of ways of assigning these, is very limited, because again, if I suppose this diagonal is not set, so I don't set it, then I have to set the diagonal coming this way, the diagonal coming this way, the diagonal coming this way. But by setting this one, I can also know if this one is set. So basically, yeah, all the squares, all the diagonals on the left squares, on the black squares in a chessboard, are determined by the first diagonal. Okay. Toggle or no toggle. Okay, cool. Cool, makes sense. So t test cases while t minus minus cool. So now we've just read the input, and we have to assign some diagonal to each element. So the idea is that diagonals, so one diagonal of an element ij is made by I plus j. The other is made by I minus j. Let's also add n here. And yeah, I guess that's it, right? Okay, 4. If mat of ij is dot, then it means that this one should should be equal. So we add an edge of type 0 between a and b, else we add an edge of type 1 between a and b. And then we'll just do some sort of traversal. Cool. Anything else that's okay? Okay. So cool. And 2 times a, 2 times a. So we have to add edge between here, right? So add a, b, 0, and here add a, b, 1. This will just add an edge in our graph, because we build like a graph of like how these depend on each other, because how to actually see the solution, how many we have to toggle, is we have to do some sort of traversal on this graph. You'll see graph which will have, let's see, this is 2n, so 4n should be enough. Let's do 4n plus 5 vertices and add two times b plus 1. This graph is also like bipartite, but that's not useful information. so I'm not sure how it can be used. Times AC. So we can either color it with call, and this will always return an integer. So this function color, or let's say compute, this function will try to color, like color, it's bad to say color, but try to fix that this node, the diagonal corresponding to this node is color is set or not. So call will be 0 or 1. Okay, we'll just do vector scene graph size false. We call if scene node, actually vector color, the graph size -1. If color node -1, assert color node call, and return. This will push a node in our BFS kind of traversal, and we also have to keep the queue of nodes. And first we'll push node with color call and size node q of I, and for each edge in the graph and edge color equals E, and then we'll push vec with call XOR equal. So just greedily color all the nodes in the graph, and at the end for each node visited, if color node is 1, ans plus equals 1, or just ans plus equals color node. And this compute function should color starting with node with some given color, and then return our answer. And the only thing that we have to do here is on black is minim of compute 0 plus 0. So the first diagonal, which is 0, 2 times 0 plus 0, we try to color the first diagonal with color 0, or try to color it with color 1. On white, the second diagonal, 2 times 0 minus 0 plus n, with color 0, 2 times 0 minus 0 plus, actually this should be the second diagonal, right? So we want to compute 1 here, plus 1 with color 1. Actually this can also be 0 plus 1. So the thing is, the only thing that we have to fix is whether or not we color the first diagonal white, or like we change the first diagonal or not, or like the diagonal right after that. That's what we do. And we just output on black plus on white. And this should be it, guys. I minus j plus n. I minus j plus n. We can just do a minus j, but yeah. A 2 times b plus 1. Should be good. Let's let's test it and see what's going on. Undeclared identifier M. Because this is not M, this is N. And I said that this should return an integer. Cool. So it compiled correctly. Let's test. Okay. It seemed like an assertion failed. And for the first test case, no, it's actually case 1, right? That is failing. So for test 1, assertion failed. Let's see what's going on here. So let's go to prob 3. So the assertion that is failing, and I hoped that it would not actually, is that its color here is not uniquely determined. Actually, this doesn't even have to be a graph if I'm thinking about it. Yeah, this doesn't need to be a graph. Like this can just be vector of int go of 4 times n plus 5, vector of int call or switch, or I don't know, switch of plus 5. And you can just say that go to is a is to b plus 1, switch of 2 times a equals switch of 2 times b plus 1 equals c. Is it correct like that? Oh no, it's not. Never mind. Okay. So it's pushing some 7 with color 0, which is it's pushing. So first pushing is 0, and then it goes to the second diagonal, which is 7. Is that right? It seems to be right. So 7 should be 0, which it shouldn't be. So here is the problem. Here, if it's black, we do like this. Seven should be 1, and then it wants to push 0, 1, which is not what we want. Int node int call equals color of node, and this should sort it. Oh, so 3 to 0, nice, or 0 to 3, cool. So I guess this is a good time to just submit, I guess. Let's just check. Okay. and then we'll talk a little bit about what I did here. And yeah. Okay, so it got accepted on both the tests, the small test set and the big test set, or whatever these two check marks mean. I'm not sure. Right, so let's analyze it a little bit and think about what I did. So first of all, the problem seemed really hard, but you the idea that I tried is just experiment with the problem. So first of all, like by I don't know, just by simulating kind of and trying to figure out what's going on, I saw that here you have a dot, right? So like if you have this diagonal and if you toggle it, then this diagonal shouldn't be toggled, and this diagonal shouldn't be toggled, obviously, because if you were to toggle both of them, then there would be a dot here, and you don't want it to be a dot. So you don't want to toggle this, you don't want to toggle this, you don't want to toggle this. But if you don't toggle this, for example, if you don't toggle this diagonal, then it means that you have to toggle this diagonal, and so on and so forth. You would realize that if you just think about which decisions influence other decisions, you would end up realizing that you have fixed all the diagonals that go on black points on the chessboard. So like this diagonal would be determined by all of these other diagonals, and so on and so forth. And yeah, so basically after you have, if you think about whether or not to toggle this diagonal, if you decide, for example, to toggle it, then it means for every other diagonal that goes through black squares on the chessboard, you know what to do with them. So in reality, there's just 4 cases that matter: whether or not you toggle the first diagonal, and whether or not you toggle the offset it diagonal, like the diagonal just to the right of it, I guess. And yeah, we've coded this. The way I like to code stuff, I guess, is I like for my functions to be kind of in line most of the time, not always, but like most of the time. The reason why I do this is that it's just easier to look at it, and like you can reason the related to the code just by looking it from top to bottom. And for me, it's useful to not jump around and not have many indirections to jump to a function or something like that. So this function just decides, basically this fixes the fact that this diagonal should be or should not be toggled. And if this diagonal is toggled or not, this will influence other diagonals on the same part. Let's say, like if these are black square diagonals, the others would be black square diagonals as well. So in order to fix them, I just compute a graph. Like this was the easiest way I could think of. I just compute a graph, which means that like if I color A diagonal, then B has to be colored the same. That's this 0 here. And here it says that if I color the A diagonal, the B color, if I fix the A diagonal, then the B would be fixed but differently. Just let me know if this code makes sense to you. Like if it doesn't make sense, actually. That's if it does make sense, that I'm happy about it. So recently we're seeing a lot of people making YouTube videos and streams. Well, I think I think that making YouTube videos is great because you can reach out to a lot of people and a lot of people can watch you, and I think it it's it's very useful for somebody to be open about, I don't know, their technique that they have developed during their time. I think like the reason why I started to do these streams is that I was kind of unhappy about how most of the people see like coding and solving competitive programming problems. Especially the thing is like a lot of people train in terms of, hey, let's do a lot of problems involving this technique, or let's do, I don't know, let's read these articles and solve problems that 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 specific algorithm solves. I think that what like the reason why I'm doing these streams in this format in particular is that I want to kind of emphasize the kind of general way of thinking about a problem, the general way of approaching a problem when you haven't seen it beforehand, and the things that you try. And yeah, I think this is very valuable, and I think it took me a lot of time to realize how valuable this is, basically. Like it seems to me like this is at least just as important as knowing algorithms, and I don't know, the idea of knowing how to do, like what to do, what to analyze about the problems, how to take some special cases, work on it, try to decompose it into easier problems, things like that. Like this is, to me, this is kind of a general process, like a general thought process that's hard to emphasize when you, like, I don't know, when you write an article on code forces. It's kind of harder to see, and a lot of the times I don't realize what I'm doing and if I'm doing stuff right, if I'm doing stuff wrong. And I think this might be useful. I mean, okay. So, should we try to solve a harder problem? This problem, I'm telling you, it looks really interesting, it sounds really interesting, but it's also, it seems hard. So what this problem is telling us is that you have an array of integers and you have to split it into k subsequences, and you want for each subsequence the difference, the absolute difference between the sums to be less than this max. Now I think it's a bit hard to visualize what this means. I mean, it seems really disconnected. This inequality seems really disconnected to everything. But obviously, like if you have kind of problems like this, maybe a good idea is to try to come up with slower solution and see if you can optimize this. For example, you have to split it into k subsegments. So usually when your task is to split a sequence into k contiguous subsequences, I mean, the first thing that I would think about here is dynamic programming, to be fair. Here it might be okay. So if you think about it, you can do some sort of dp of, let's write it somewhere, dp of ij, right, from the first I sub I elements, I made j subsegments, whatever. And let's say this dp of ij is, for now at least, it's 0, 1. If let's dp of ijk. 0, 1, if I can do that. I make j subsegments and the last. So actually let's do, oh, I see. Let's do, I made I subsegments, and subsegment I consists of jk. So that's the first dp that you could think about, and the dp will hold 0, 1 if I can do that. So if I haven't broken this thing. Now, how would you go about in a transitioning? So what would be the transition? dp of ijk would go, so would transition into dp of I plus 1 and k plus 1 and l if sij, if jk, right? sjk minus sk plus 1 l less than or equal to the maximum. Wait, this I'm seeing something here, because like you have the maximum of the ith segment is mi, and so like the max of mi and mi plus 1 is actually the maximum of the max of s max of a I through L. See, because like you have two maximums here which are adjacent, but like the maximum of two maximums calculated like this can be just written as the maximum on the subsequence, like subsegment. Maybe this is useful. I don't know. I'm not sure. SJK. So the absolute is less than this, which means that basically you have to, like, if you have absolute value, maybe this is useful, I'm not sure. So like you can think that I'm thinking that if absolute value of x is less than or equal to some value which is positive, this is positive, it means that x and minus x, right, this is equivalent. And this s of jk, what's like in terms of partial functions? Let's call s of something as partial function. Sk minus sj minus 1 minus sl minus sk. So what did I say? This has to be less than and the other around, sl minus sk minus sk plus sj minus 1. So this is 2 times sk. We'll just rewrite and see if we can do something with it. Times sk, yeah, this should have been a plus here. So yeah, that's right. So it's like this is actually the absolute value of sl plus sj minus 1 minus 2 sk. Okay, so the thing is, like, if we have segment I through j here, and I through j here and j through k here, j plus 1 through k here, you want to, like, if you want, I'm thinking, like, if we fix, let's say we fix I and k, right? Where should we put j? Do all candidates of j matter? It seems like they don't, because, like, if the maximum here, the value on the right is the same wherever we put the j. The only thing that matters is the absolute value here. So it seems like there's only one. I argue that there is one candidate. So there is only one candidate worth looking at, which is kind of like, I would say kind of like some sort of median value of the partial sums. So it's like where you have an array of increasing elements, and you have to find out where, like, some on the left and some on the right are as equal as possible in order to minimize this left thing. Cool. I think we're getting somewhere. I'm not exactly sure where. Values are small. I guess this doesn't matter so much. Let's do some other thing. Let's see if we can do it in k. Can we do it in k plus 1? Can we always do it in k plus 1? So we figure out what the best j is to minimize this sum. We put j here. Oh, there is one thing that I haven't considered, is the fact that this j actually matters because the next sequence must start with that j. Yes, I'm kind of confusing. Yeah, when I say subsequence, I mean subsegments. The thing is, like, in Romania, we kind of use a term that is very similar to sequence to account for, like, contiguous subsequences. So yeah, I'm sorry for misguiding you if I have. So yeah, I'm referring to subsegments. It's always subsegments. Whew. Okay, hard one. Hmm. One thing that might matter is the fact that all elements are up to 50,000, which I haven't used yet, and I'm not sure how to use it. I mean, if all elements are up to 50,000, it would imply that the difference between partial sums, like if you think about partial sums and you look at two different partial sums, two consecutive subsegments, the difference between, like, they should differ by no more than 50,000. And you want to see if you can split it into k subsequent and also output solution, right? Always. Always output solution as well. Nice. Is it always possible? Is it always possible? Maybe it is. How cool would it be? I mean, there's only one example and the answer is yes, right? So it might always be possible. We could check it. I mean, we could check it, but maybe we can actually prove it. And we try to prove it by induction. So suppose maximum is on right. Now we can always split any prefix. Okay, -1. So it's okay with any prefix. Let's do some quick test. Or right now I'm thinking whether or not it's worth making like a brute force implementation of this. This would allow me to check if it's actually always possible, which would be a little bit relieving. I mean, it will tell us that we're on some sort of a track. So I guess, yeah, let's do probe for.cpp. So remember, I'm just writing a brute force implementation here. So okay, so let's do partial sums. So s of n, okay, the size for k is up to n, right? Actually, I think I might not need it. So jk, okay, k equals to j s l from k, right? Plus equals v of k. Jk, if not okay of ijk, continue, and this will be our dp. So it should be okay of ijk. Okay. I up to n, j up to n. If not okay, and okay of 0, 0, 0 is actually we would have to do from 1. So for int I from 1 and for 1ij is true. Cool. I missed some parentheses, seems like, because my editor is screwing with me. Okay, so this is like the dynamic that tells us if we can split into I, like into first dimension is the number of sub segments, the second and third dimension code the last subsegment. So here it's not actually okay, thank God. This should be I from 0 to n plus plus I. Okay of 1, 0, I is true. Cool. And j here should be from, I mean, it's fine. It's fine, I guess. K from j plus 1. Okay. K from j. So this is jk, this is the first thing, and then L from k plus 1. That's fine. Oh, okay. So if abs s1 minus s2 max m1 m2, then it should be okay of I plus 1, I plus 1, j plus 1, L, no, k plus 1 here, k plus 1, L should be true. Cool. Now let's test it. Okay. So all values should be true. Which value should actually be true? It cannot be true, right? It I should basically assert here that the hell. That's fishy. That's fishy, I'm telling you. So yeah, this is basically checking that we always have a solution. So it doesn't take much to code. So I guess I went up for this path. Maybe let's do brute of v. And we don't want this to return anything. Let's make sure. Is it right though? So the thing is, like, what I did right now is I wrote a very quick brute force, like, dynamic programming that would try to come up with the solution. And basically what I'm checking is that you always have a solution, and it seems like you do have a solution. I mean, I hope that I didn't mess it up. How can we tell that? So I can do a break here and here, and output for I for I ranges. We have solution with j plus 1. Let's see what this would output. I mean, I am really surprised that it's not breaking, so give me a minute. Okay, so it seems like for one range we have solution with 1, which makes sense. For two ranges, it seems that it's starting at 3, which has 3, 7, 6. This has an 8, so this works, I guess. And for 3 ranges, it ends at 5 and does 6, 7, 3. Okay, 8, 2. Yeah, guys, it seems like we're onto something. So first thing that we notice here, just by making this brute force, which was not that hard, and like a quick test checking, is that there is always an answer, which means that we can use like our tools for our awesome tools for how do you call it, like induction and stuff like that, to try to sort it out. Now, also, what you can notice here is that what I'm outputting here is always increasing. So this kind of tells me that maybe there's some monotony to it, which is expected in this sort of scenario. Like, if you have low k, your last range you would want it to be longer, right, to have a bigger sum. But as k gets bigger and bigger, you also want your range to go closer and closer to n, which makes sense, right? So what happens if we binary search? Whew. And what would we binary search on? Like, one thing that I'm thinking that might work, or maybe not, is if we binary search on the element, this would fix our sum, and now we just do some greedy to fix the others, and see how many elements we have picked, like see how many groups we have made. And my intuition is that the number of groups would be always, like, if you choose the first range to be small, right? If you choose the first range to be small, you would have a big k at the end if you do just the greedy approach, which I'm not sure what that is, but I guess the greedy approach would just do, I don't know. Yeah, I mean, so let's say we have fixed the length of our first range. Now we can choose, now the second sum can be in some range as well, for some reason, it seems. Okay. And it seems that you can also binary search on the second one. Does binary search do anything? By the way, guys, I think I know solution in n squared now. Because this OK thing is like if you want to compute k, if you want to have k subsequences, then it means that the first length, like the j, the first range, the first subsegment should have length between some a and some b, and you can do dp to compute these. By using the fact that there is always solution, of course. If k were to be small, like n times k is definitely doable, I'm telling you. Not very many choices though for the next one. Let's just make sure that it doesn't fail. It would be silly if it would fail. Just run it a little bit. Cool. Okay, let's do some different thing. What happens if we binary search on the length of the first segment and then we just do greedy? What could happen with our greedy? What could happen is, like, if we choose always the shortest sequence that is possible, okay, so let's do solve, or like let's call it, oh, this is different task. Prob 4. We have brute, we have test. Let's do actually a solve. So int n, which will int n k, which will read. We read the input. And now we binary search. So int b equals 1, e equals n minus a length is n, while vkm uh, k minus 1 space separated integers. Okay. Actually, if I think about it, I can do something like this. M solution. If n size equals k, return solution. If n size is less than k, then it means that we have overshot, right? So if answer yields less than k elements, it means that our m is too long. So we'll just set e equals m minus 1. Else b equals m plus 1. I hope I haven't screwed up one of one of the easiest things in competitive programming, supposedly writing binary search. So yeah, assert false. Cool. This should be okay, and now we don't need solution anymore, and we can just have the overload of this function solved. That will solve it for a fixed vector of int v int k int l. So first thing has length l. And now we do greedy. So we greedily pick the smallest thing. So yeah, 4. S1 plus equals v of I, v of at m1 max m1 v of at plus at long s1 int m1. Cool. And now for int s2 and m2. Now we'll just do greedy and try to yeah, Do we need max on range? And yeah, I think we might need range maximum query. And do we need range maximum query? Let's actually do range maximum query. So I will not implement this, as you probably have guessed it. We'll just be tricky about it. The thing is, like, the algorithm that I'm trying to do here is first fix the first k elements as being the first subsegment, and then keep, like, greedily pick the shortest subsegment that I can. And after k iterations, this might undershoot. Like, if after k iterations this overshoots, then it basically means that we cannot, like, I think that we cannot solve it if we have fixed that length L and k elements. And now if it undershoots, I will try to move the first, like the last thing, I would move it at the end and kind of try to how do you say, try to calibrate the pointers. You'll see what I mean in 1 minute. But for that, it's easiest if I just use range minimum query. So let's do it actually range maximum query, right? And I would have to do here max and here max. So this is now range maximum query. Cool. So I will just keep a RMQ of values, and yeah, let's also do struct sums, whatever, sums const vector of t v. long s for size s of n. Cool. And do n. We'll just do partial sums and query. Oh, yeah. S of b if a minus 1. Cool. So now we have this whatever, int, no more t. So now we have RMQ v and sums. Oops, where am I? What did I do? No, what did I do? Sums v and k and l. Cool. So now I need RMQ and sums. RMQ of v, sums of v. RMQ sums. Cool. Cool, cool. And ends at L. J equals n spec J plus plus J if it's at -1. Okay. Sums dot query of ends size -2 ends size -1. Query ends query ends size -1 and J in M2 is RMQ. What do we put here? We put J plus 1 and break. And here we want from I equals 1, and here we expect and size. Actually, let's do it like this. Okay, if n size is less than k, then what we will do is we'll return ends. Because like, okay, quick recap of what I did for until now. Ends erase ends begin, right? Okay, what I did until now is I've just like I'm fixing that the first segment is L, and after that I'm just greedily choosing the shortest interval that I have to append it. And my intuition is that if this is less than k, obviously then we cannot do it with L, with this L, so we have to choose a what, a bigger L for our algorithm, which is what we will do here. If ends, we have to choose a smaller L, because like we didn't have enough segments with the shortest segments greedy, and now n size is k, which means, for example, here if n's back is equal to n, we're done, right? But unfortunately, this is not always the case. And if this is not always the case, then we will just try we will try to change, like we will do n's back equals n, and n's back equals n, and here should be -1. I just realized. So here also -1. Okay, we'll do s back equals l, and for I from size equals k plus 1. Okay, for I from k minus 1 to 0. Yeah. So what do we want to do? Now we fixed the last interval, and we have to toggle it to fix this like a little bit to the right. So while query of ans of I minus 1, so I ans minus 1 ans of I minus 1 RMQ query ans of I minus 1 ans of I minus 1 sums query ans of I plus 1 minus 1 ans of I plus 1 minus 1. And now if s1, so if this is okay, so if abs of s1 minus s2 max of m1 m2 ans erase ans begin and return ans, because we have solution. And now we will try to increase the pointer, so plus plus ans of I if ans of I equals ans of I plus 1, we would have to return what? Push back minus 1. We'll just return a bigger vector if that happens, because here I'm checking against the size, like if the size is equal to k, then return solution, and if size is less than k, then go there, go left, and then go right. Cool. And now, yeah, now I would want to whatever. Okay. Let's remove this. We'll just do it in the end. No. And size is equal to k, and then return solution. Ans pop back return ans. Okay, so this should be a good solution. I mean, I'm not sure if it's the good one, but we can try to see what's doing. I mean, okay, we have mismatched brackets. Nice. So my code is actually not even compiling. I didn't even bother to check that my code in my document compiles. Oh god. JMP. And this is called RMQ. God. This code should actually be checked. Oh well. '92 has an error. Spec up until n and size. Undeclared, and so we have problem with at 88 141 88. We don't need that anymore. 141, because it doesn't set false. And we also don't have n in the big solve function. Will this work? Probably not. I mean, we have some undefined behavior in 188. Oh god. -1. So what happened here is I'm querying stuff on bad ranges. So maybe what I'm trying to do here is L-1 and just do +1 here, +1 here. Let's check this, and we put J +1 if it's good. J, and we put J +1 here, +1 here, and it should be okay. Okay, so always make sure we query with +1 here and nothing here. +1 here, nothing here. +1 here, nothing here, and nothing here, and +1 here. Do you think this will work? No. Okay, line 88. Round 2. Okay, so the problem is here, is I want to put n. Do I want to put n or n-1? Wait, I'm putting the last index, right? So here I'm putting J +1 for some reason, whereas I would want to put I'm putting where it ends, right? So here it ends on L-1. So if I want to go 2 plus 1 here and put j here. That's cool. And n minus 1 here and n minus 1 here. And this is where it ends, right? This is where the actual thing ends. So yeah, let's try it again. Run it. Oh, it does something at least now. So it says 2, 3. Is it correct? I mean, it seems that maybe, but probably not. Actually, is it actually correct? Let's put something different. Let's put 5, 5, 1, 2, 3, 4, 5. Okay, so the thing is what I'm outputting is from 0, and we want to add 1 to each element. That's the first thing. So once we fix this, oops, problem 4. Once we fix this, we should be able to see 1, 2, 3, 4, even though input is not what I wanted it to be, but and for this I am seeing 3 and 4. Is that correct? It seems to be correct. Is it though? 3 and 4. The absolute difference here is 34 plus 18. So it seems to be good. Let's actually check that the solution is good, because we can, and do the assertion here. That's what we are going to do. For int I equals I0 through k plus plus I from 1 to k. Oh, we erase as begin, right? So let's this is where it ends. I know this is not great, but for I from 1 through to k, we would want to check. So boom, boom, boom. Okay, so if this is greater than this, assert false. This is how I will be checking. Okay, so this is working. Let's do the same thing with 5, 2. 17, 18, 17, 30, 35. Yes, 3. Cool. So now the good thing is that we have this test function, so we can just do, instead of brute of v, do solve of v, and okay, rent n plus 1. Okay. Okay, we have an assertion failed. Oh, haha. Hard problem, hard problem. So k is equal to 6. One, 1. So n equals 1 fails. Nice. Okay, 3. So n is at least 3. Let's fix this. N plus 3. Cool, cool. Oops. Prob 4. Not great, not great. Ah, God. Let's try to find a smaller counterexample and work our way from it. 5-1. K is at least 3. N minus 3 plus 3. Is it okay? It can be n, right? I want it to be n minus 3 at some point. So this is what we're going to do. 6, 3. 2, 5, 8, 2, 4, 9. Let's output also the solution and we'll work through it together. Where am I asserting false? Here. So it says that it's doing 0, 1, 3, 6. So it's ending at 1, at 3, and at 6. And what is incorrect about this? The fact that oh, I see the problem. Oh, I see the problem. So yeah, it's just a little bug that I introduced here when I am doing the solve. Here I'm solving from k minus 1. So when this is okay, when this is when this is okay, I don't do this. I just break from this while loop. That's what's causing it to fail. This is what I want. So if this is good, I just break from the while loop and go to the next step. Five, 3. This is failing again. In line 140, let's see here. So line 140 is failing. Assert false here. Oh, yeah. Six is not working. Oh man, nothing is working. Line 178 is failing here. It's failing here. Why? Well, for 6, 6 it should be fine, right? Let me think about it for a minute. So yeah, let's do this. Let's do solve. V is 4, 10, 1, 6, 3, 3. Solve this. This is V. Test V. TV and do const here so that I will sums of TV, and I want to give it as a parameters k equals 6 and l equals 1. Let's see what this solve is doing. And true. True is it will mean that bool verbose or debug false. So actually we don't need debug here. Let's auto ans for auto x ans x plus 1. Sums query. TV. Zero, 1, 2, 3, 4, 5, 6. So it seems to me that it's outputting this correctly. So maybe what's going on here is so maybe my binary search is not doing the right thing. If n size is k, we output. If n size is less than k, which this is also outputting a 0. Oh, yeah. My bad. I forgot about this. Cool. Let's continue testing. Oh god. Oh god. I so hate myself right now. Okay, so apparently I am outputting 0, 2, 4, 5, 7. So for k equals 4, I'm outputting 2, 4, 5, and 7. And this is not right. Why? 2, 8, 2, 4, this should be okay. And this should be okay. And this is not okay. This I think it was a bug, right? It should have been a bug. But it's not. It's not helping at all. Okay. So what's happening here is it seems that this algorithm is supposedly, so it's outputting this solution, but the thing is it's not the correct solution, and this assertion false that I put here means that I'm actually outputting a bad solution coming up from this thing. Maybe what is happening. Let's actually kill all this. We don't need this. Okay. So this fine tuning that I'm doing here is not working as intended, and I'm not sure why. I would have to look into that right now. That's very odd. This is what I'm outputting, what this solve is giving me, and this is 2457. So 2457, and for some reason it told me that it's okay. And here I'm looking at +1 +1. Okay, so oh, I see. I see. So yeah, this is actually not really correct what I'm doing here. Like this fine tuning is not correct. Is there any way I could fix it though? Well, one way we could try to fix it is do some while true. Do something like that. I mean, would something like that work? I guess. I guess it will. I mean, okay, now it's working, but it's probably not in the time limit, because probably there's a lot of changes here. So this is like big O of n squared algorithm, which I'm not sure it will pass the test cases if the test cases are strong enough. But hell, I mean, we've wasted so much time on this on this implementation that we might as well try to submit it, right? I mean, is there anything to lose? Probably penalty points. So yeah, I would actually try to submit it and see if it actually passes. I would not be surprised if it passes, to be fair, but it's not the correct solution. Please run past test 1. Thank you. Whew. I mean, we have big O of n squared log n, right? Time limit exceeded on test 2, so test 2 was good enough to kill our little change here. Is there any way we could... I think... I mean, I could imagine how it could be done. Do you guys have any ideas? So what I try to do here is, obviously I figured out that first I figured out that there is a solution no matter what. I mean, there is always a solution, and you could get to the solution by kind of binary searching for some k. I guess one way that we could try to fix it, like we're binary searching on a k, and I think one logarithmic factor could be avoided here. And yeah, adapt. Or not adapt. And k and false, not adapt. If n size is less than k, then e equals m minus 1, else check equals m, b equals m plus 1. Wait, I want the biggest k. Yeah, I think that might do the trick. And here, solve RMQ sums vk as true. Pause. True. Cool, so it's still working. It's still working correctly. Let's check it for n equals 10. So it's still working correctly, and probably I removed one logarithmic factor from this, but it might still be not enough for our purposes. So, but yeah, let's submit it anyways, because we're running out of time. Time limit exceeded, please. You see, the funny thing about Codeforces is that when you are failing a test case, you know that you're failing a test case, but Codeforces just lets you, just gives you the running verdict a lot. It's a bit annoying. So the thing is, like, this the binary search is okay, but this adaptation is not okay. What I'm trying to do with this adaptation is I'm trying to kind of fix the fact that my greedy algorithm just outputs up until some position. I have a suggestion. Maybe instead of big O of n adjusting, we can pre-compute for each index closest index on left, which is good. Yes, but the thing is that it depends, like these good conditions depend on three things, right? It depends on like the right right position, the left position, and the middle position. So it's kind of like you would have to do them kind of in parallel. So one thing that might be it, just let me think about it. One thing that might be correct here is if we do some sort of two pointers technique. Let me think about it just for a moment. So this is all, and we've computed solution for something less, and now we have to add these things as well. And to add these things as well, we add this to this, which might make this sum too big. So this sum might be too big for this maximum, so we have to make it smaller. I wonder what happens if when we do adjusting, instead of adjusting until it is good, we continue adjusting it as long as it's not bad again. So like so state equals 1 and ans of I plus 1 equals ans of I plus 1. If state is 0, we do this old stuff. If not, we break. Else, if state is 1, we do minus ans of I and we break. If so, let's see how to populate the change variable as well. So if int state equals 0, if and if it's the first time we're here, we just break. If not, we go to state equals 1. Okay. Now else, if state equals 1, we do we minus minus, we decrement ans of I and we break. And now if ans of I, now we want to increment it. So if ans of I equals ans of I plus 1, and now if not, we do plus plus ans of I and we do change equals true. and fst equals 0. So this is like the adjusting portion. Let's see if this compiles and test it again. Oops. It's still working. Now the difference is that, so the difference, what I did is when I'm adjusting, I'm moving the pointer right, okay, but I'm moving the pointer right as little as possible, but maybe the solution is to move the pointer to the right as much as possible. Maybe this will reduce the number of changes. I can actually compute the number of iterations, and yeah, let's do iterations and do and see how this changes. So oops, let's also test it and see. 1 or 2 iterations. Oh well, sometimes 2, sometimes 1. I'm not sure what happened if like beforehand. Let's put values to the, it seems that there's very few iterations that are happening. I'm not sure if there were many before because I haven't put that check, which is probably something I should have done. But now it seems that on random test cases, at least there's very few iterations. Also, random test cases probably aren't good enough for this task, so yeah, it will still time limit on test 2. Oh, quad forces. Yeah, so no idea. No idea. There obviously, like, I think the solution is okay. I think it's good to binary search for k, for that k, and try to find this thing, but like this adaptation, this like switching from yeah, this like fine-tuning of the solution is probably what's killing this, is not correct. We can, yeah, it's sometimes it has 3 iterations. Maybe I'm doing something wrong, but I don't think so. The maximum doesn't change on those, so hmm. I think, guys, I think one thing that we can do is like we can have the algorithm that computes the shortest, like the like that's greedy for the shorter things, like stops at the first one, and then the algorithm that stops as long as that makes them as long as possible. And after we have found our k here, we will just do another binary search to figure out when to switch between the two algorithms, something like that, I think. But I am not sure. I mean, there's like where to switch between the two algorithms and how much to take. So you'd want the first k, like up until some position, to take via the first greedy, and then take up until that, like when min and max, if you were to do min and max would meet, you would do that. I think we can do this. Let me try to do it. So like this adaptation is obviously bad. Okay, let's kill it. Okay, and now what I will be trying to do is yeah, it's happening. I will be changing and I will just copy all of it, and not adapt does not exist. If this will be what is returned by this solve. So I'm going to copy this solve function, and now what is happening is it will have an extra parameter int pos, which is the position from where we'll switch to the first, from the first strategy to the second strategy. So let's see. So if at position pos, you will switch between first strategy and next strategy. As long as possible, and then as short as possible. So okay, so yeah, it's I think I'm going to, so well, I have a little bit of an idea, but I think I'm a bit I'm a bit tired to code it. So the idea would be like this. So this greedy would give us a prefix on which we can complete, on which we can have k segments that would cover a prefix of our array, and we can also have another strategy that would that would pick the long, like this is picking the shortest things and going up through some position, and then another strategy would pick the longest things that would just come. And in theory, I think you could binary search on when you would transition from the short strategy to the long strategy, like when you would transition from going short segments to going long segments. Other than that, I mean, it's certainly doable to do this, but I'm not sure exactly about the implementation details. And so I think I will wrap it up here, and I will let you guys know. Like I will try to solve it on offline, like try to implement this strategy of changing this implementation of changing the strategies with binary search offline, and I will let you know if it works, I guess. So it's interesting that it goes time limit exceeded on test 2 in the, yeah, given that, I mean, yeah, I guess one thing that is not, like, it doesn't hurt to try, I guess, is just do some stream desynchronization. But other than that, I'm not sure. Like, the test is not being used. Comment this even though it doesn't matter. I mean, other than that, I have no idea. To be fair, let's make sure brute doesn't run by some horrible mistake. But probably not. Sums. That's in I mean, stream desynchronization might help on code forces, but probably not. I mean, I'm not sure. It's good test cases. What can I say? Yeah, not helping me. Okay, yeah. For now, I'm not sure what is there to be done to further to make this thing a little bit faster. I mean, maybe give it some big test case. Yeah, let's see. Yeah, whatever. Hmm. Oh. 0.5 seconds. I mean, it's not great. Not bad as well. I think I'll just give myself, I don't know, like 3 minutes until 30, and if I'm not going to solve it, then we'll wrap it up here and I try to solve it offline. I mean, for now I'll just try to see if I can somehow optimize some stuff here, basically. This is not correct. I mean, this RMQ is not correct. I should really change it. Okay, partial sum seems correct. This part seems correct. Then adaptation probably is incorrect. I mean, probably it's not great. Let's see. This might actually be the good solution. So I think I actually figured it out. Or no? I mean, okay. And what happens if I do? Ooh. 0.5 seconds. Not bad. Yeah. Not exactly sure how to solve this problem. So yeah, it's still time limit exceeded on test 2. So yeah, I think I'll wrap it up here. I'm sorry if you thought I would be able to solve this problem, but I didn't. I will try, as I told you, I will try the strategy, the switching strategy offline. And yeah, I mean, if you liked it, let me know, like in the Code Forces blog. Tell me what you think I should be doing next if you have ideas. But yeah, I'm not exactly sure about this problem, and I will try it offline. Thanks a lot for being along with me in this stream, and see you guys, I think, either next Sunday or in 2 weeks. So yeah, let me, yeah, cool. So yeah, let me know in the comments if you liked it. Press the like button on the stream, and see you again next time.